to make sure that everything is synced up because there are a ton of files in the new lesson folder. So what you're always going to have to do is before you ever go through the process where you merge one branch to the other, like merge my branch into yours, you're going to have to commit the changes that you have in your repository. So if you haven't done this already, you should open up GitHub for Mac and click on Changes, and then you should see you should actually see a bunch of green here for you. Have you all done this yet? Synchronize your repository. So in any case, what you should do is type your commit summary here and say commit to master. And then you can go to branches and do this weird process of synchronizing the updated lesson on the remote repository to your fork. So I actually don't know what is going on with my repo at the moment, but I'm going to check. Okay, some of you encountered a situation where you had made a change to a file that wasn't yours, another file in the repository that was maybe part of the core information of the course. Like if you opened up the file for the assignment and you hit save while you had it open in Xcode, then you got you maybe erased the view controller that was in there and saved and closed Xcode, and now you can't get it back. Git actually gives you the ability to undo changes that you've made to files on your hard drive. So the way that you handle that is you're able to go into changes and find those changes that you've made, whether it's an alteration to an existing file or a deletion, and you can right-click and say discard changes. What this will do is Git is actually storing your entire history of saves to the hard drive, deletions, and new files. You can undo those changes. So if you ever make a change to a piece of course material or a sample that's been given to you and you want to get back to where it was, you can use this command to do that. Does that make sense? So discard changes and then discard changes, and that will go away. And now if I show you the folder on my hard drive, that file has now returned. It has been resurrected from the dead. Yes. So despair not. Git will save you. So I'm actually going to try to do that for everything. Actually, I can't do it for all of them. So, no, you actually have to go and save that later.
So that will fix the branches and the merge and everything.
I'm sorry?
We're just doing
Yeah, so after you commit, then you can sync. And that will ensure that you have all the latest information, both from your fork and from the original repository. And now you can go through this weird process of merging the repository into your fork, which is here. So updated lesson 3 PDF, that's the one that we want, and then you just put the place where you want to put it, which is your branch, merge branches. And now if you go to your and then then you hit sync, and now if I go back here and I go to lesson 3, now you should see all of these files in your lesson 3 folder.
Sorry, in terms of committing our changes to the assessment, even if it's not done yet, we should still do that.
Yes. It's also a good way to get into a habit of placing checkpoints if you want to in your process to say like, oh, added navigation controller here, commit it. Added a new view controller here with my bio, commit it. Like, if you get into that kind of workflow, that's more of how developers tend to work with their code. If they're being disciplined and good developers. Of course, it's very easy to fall into a trap of writing a ton of code and then running some random git command and losing all of your changes, which happens sometimes. It's very painful. Although I don't always recommend to put a Git repository into Dropbox. Sometimes it does help. Okay, so keep this folder open. We're going to be interacting with this quite a bit today. Does everybody have these files on their hard drive? No? I'm sorry? Yeah, it's not good because like Git repositories have thousands of files in them, and it becomes very difficult to synchronize with Dropbox. And if Dropbox encounters a conflict just because of two computers that just happen to be slightly opposite, yeah, exactly. And it'll name your files like deep in the Git repository, and you have to manually fix them. It's terrible. Okay, so who does not have these files in their lesson 3 folder? One here, and there, 1, 2, 3. Okay, and you do not have them? No, I have. You have them. Okay, everybody else has them? Okay, so did all of you run through this merging step? Like synchronize, drag and drop, then merge branches, and synchronize again? And it didn't work?
My one on the bottom isn't updating for some reason.
It's not updating? Even when you go to repository pull?
Yeah. As of April 23rd.
It doesn't say updated lesson 3.
I feel like it's the same thing that happened last week, but I didn't do that. I didn't merge them wrong. Remember this happened last week?
Yes, I remember. Drag. So I think what we're going to have to do is we're going to have to pair up and go through some of the material. Actually, wait a minute. You're all on Slack, right? Okay. So what we're going to do is we're going to deal with this later. And what I'm going to do is Slack every playground file, and I'll zip and Slack it so you can get it straight from there. Okay. Because this is not a problem that we should solve right now. Yes.
So I just did the whole process on the command line and it went through, but when I tried to do it on the app,
Yeah.
it said that everything was synced, but it wasn't.
It hasn't. It's not synced.
Yeah, so I think that is the app. Because I just did the same process and I pulled everything that was new.
Okay. But you pulled from you just did a straight up Git pull.
Yeah, then it did pull from upstream.
And then from upstream.
Yeah.
Okay. And then all the files ended up on there. All the files ended up in the folder.
Yep. So I see this.
So we can do that. Okay. So it was just you just did git fetch upstream.
Well, they had already committed, so I just did a git pull.
You did git pull. All right. So all of you that are having this problem have you all committed your changes? So when you go into changes, it doesn't show anything on the left.
Yep.
It shows a conflict.
You have a conflict? Oh, gosh, this is so terrible. All right. Yeah. I do not want to deal with this right now. Because all of you might have different, like, this process won't work for you. It might work for you, but it might not. It will probably work for you. So somehow we've gotten into a state that is not going to be easy for us to recover from as a whole. So what I'll do is every time a new file need for a new file comes up, I'll place it on Slack, download it, unzip it, and we'll go for it. Okay. So as a note, those of you who have programming experience before, there is a cheat sheet here. So it's a PDF that has the entire lesson material already laid out. So it's essentially a syntactic guide for Swift for the entire lesson today. And it'll stop at function calls. Like, in other words, it will not up to but not including functions. So if you want to get a head start in playing around with the syntax here, please open that file and go for it. And I will post that to Slack right here. Everyone else, you can take a look if you like. But I think what we're going to do is, what today is going to be about is your first introduction to Swift. So we're going to pull away from Interface Builder for the day, and we're actually going to start talking about the fundamentals of the code that you're going to be using to power your apps. So we're going to talk about what Swift is in general, how it's a little bit, again, about how it's different from Objective-C, the traditional language of Apple app development. And then we're going to go through one at a time all of the fundamental topics, starting with data, values, and types, all the way to control flow, so loops and conditional statements. You're going to learn essentially how to write recipes with code. So today is a landmark day for those of you who have done no coding before. Congratulations, you've made it this far. Some of the information that you're going to be getting is applicable to other languages as well. Swift is actually a great, I think, and I think Angel agrees, is a good language to learn first because it's modern and because it has a bunch of paradigms that apply to other languages. And what I think our approach is going to be, having digested some of the later material now, is to expose to you those patterns that are most common that you're going to be using both in app development and in other settings, and try to leave some of the advanced corner kind of edge case features of the language to later, probably after the midterm, so that you get fully faciled in how to write mainstream Swift to begin with. So, all right. And the format, so we'll note about the format of today's lesson. There's going to be a bunch of playground files in Xcode. We're going to be going back and forth between the slideshow and Xcode, one topic at a time. And there's a bunch of these files that you can interact with. So those of you who have programming experience, do try to stay with us. Like, just be aware of what's going on. We're talking about variables and for example, if we're talking about variables and constants, just sort of, pop your head up and make sure that you're not missing stuff that would be important for you to know. But otherwise, you should just play around, look at the exceptions and the errors that Swift gives you when you try to do crazy stuff. Just have as much fun as you want. But the rest of you, I'll try to keep things explained a very kind of clear and paced way, so that I don't lose you. But if you do get lost, please speak up, because it's so important that I know that certain concepts you've at least digested to a reasonable comfort level for today's class. This is the class where things start to get a little bit intense, because it's new material, it's new ways of thinking. It's essentially learning how to speak a foreign language, and you're going to do it in a couple of days instead of like 4 years over your college experience. So, are you ready? Yes? Let's do it. Okay. Today, define Swift and its value to the iOS ecosystem. Define and demonstrate playground files. So we've talked about 4 files that end up in Xcode apps. And now we're going to talk about playground files, which are actually specific to Swift. They let us talk about Swift outside of the context of an app, so you can just deal with the language itself. Talk about what we call Swift's fundamental data types. So, and then using what we call variables and constants, which are ways of storing and talking about data. Applying optionals, understanding when to use them. I'll explain those later. To those of you that are facile with other programming languages, this is also a new concept. This concept doesn't really appear very often in typed languages like Swift. And then talk about this notion that we call control flow. So this is how we actually start to define that recipe-like logic that we're going to be engaging. I'm going to skip over that. Okay, Introduction to Swift. Swift is a new language that Apple has developed in recent years for iOS 7 and beyond, and OS X, Mavericks, and beyond. Those of you that are programming savvy, it's object-oriented, compiled, safe. We'll talk about what type safety is later for you guys. It was designed to support this notion of a playground, so an interactive environment where we can play with Swift and get instant feedback. And it also works in tandem with Objective-C. So, to talk about this word compile, I want to focus on that one for just a second, because that's a concept that you're going to be wrestling with a lot. Swift is what we call a compiled language, as opposed to a scripted language or a scripting language. When you're running a scripted language, or sometimes we call it an interpreted language, it means the computer is running through your code one line at a time, using your code as a kind of cue of what to do. It's looking and checking all of your logic and trying to ascertain what you mean by those symbols, and one line at a time. It's a very careful process that it goes through, and it's relatively slow. When you compile a language, when you compile a chunk of code, what that means is there's a pre-processing step that happens before the app actually runs. So in that step, what's happening is this piece of software called the compiler is looking at your code, and it's generating new code from that. It's generating code that speaks the language of the computer. It's much what we call closer to the metal. It's the language of processors, it's the language of memory, it's the language of everything that goes on inside the box, which is your computer. And the reason why it does that is that generated code, that abstract, unreadable chunk of binary blobness, is a much faster version of your app. So that's the thing that you actually package up and send to Apple, is this chunk of binary code that runs extremely fast. So your code is human readable, but in that compiling step, it's producing something that's machine readable. And actually, every time you've hit run, when we've run your apps, it's been doing that step. It's been creating that fast code. It's important because that step doesn't always succeed. It can sometimes fail. You can run into situations where you've told it what it considers complete nonsense, and it will warn you about it in the most graphic way. Then, when you run the app, things can also go wrong there. So there are two places where things go wrong. It's good for you, actually, because you have a greater probability of making apps that run well if you have that step that tells you stuff is wrong before you deploy the app.
When it's an interpreted language, does it not get turned into a different language before it runs?
Sometimes it does, sometimes it doesn't. That's all I can say. Ruby doesn't. Python does. Python has what's an intermediate binary form that it writes to your hard drive, which runs somewhat faster, but definitely not as fast as Swift. Does that make sense? It's just it's a gross distinction that I'm making now, but there are some finer details that actually blur the lines. But we can talk about interpreted versus compiled. There's this notion of being just-in-time compiled, which is Java and JavaScript. So when you run the code, it figures out a faster version as it's running, that kind of thing. So that's hot stuff. That's like super ultra modern, like coolness, which I love to talk about. But in any case, Swift versus other languages. So that sort of fits the topic of this. What this slide is supposed to be about is how does it fit into the ecosystem of all of these other languages. Swift is relatively easy to read and easy to write versus other languages, which gives it a step above and beyond Objective-C. Objective-C, you end up writing 2 files for every 1 file of Swift. And those two files have different semantics. You actually have logic in one and like essentially write a contract in the other about how that logic is supposed to interface with other pieces of the app. It's very tedious. It's very detail-oriented. Swift takes all of that hard stuff and kind of shoves it under the rug. So all you have to worry about is your app logic and some of the details and quirks around how Swift works. Swift in general, however, is a play by Apple to enhance the developer community and the developer experience. If you think about when the iPhone first came out, it wasn't just about phones, was it? And the people that use those phones. It's about a whole ecosystem of developers, marketers, users, reviewers. Just think about the entire industry that exploded around iPhones and now around smartphones in general. And so developers are a key piece to that ecosystem. They're the ones that are producing the apps. And so they're simultaneously trying to find a better way for developers to do their jobs, but also start to expand who can become a developer for iPhone apps. That's why this course, in fact, exists at all. Mobile development wasn't a thing in GA until Swift came out, because Objective-C was just too damn hard to teach in a very short amount of time. So when we talked before about being guinea pigs, round 3. So anyway, any questions about Swift and the ecosystem that is Swift and what we're about to dive into? I know it's super general, but it's kind of important to understand the context in which it exists. No? Good. All right. Let's talk about code in general. It's kind of a cliche, but code is like a recipe for a meal. It's actually kind of strange how similar a recipe is to how you write code. So the computer, the way that it executes your code is it starts with the first instruction, the first line of code that you write, and runs it, and then completes it, and then moves on to the next one right below, and runs that, and waits until it completes, and then continues on one line at a time down the chain of instructions that you write. So unlike a recipe algorithm, we have to be much more specific than a typical recipe for something like chocolate souffle. Computers are really fast and they're super dumb. They just do exactly what you tell them to do, even if that thing that you tell it to do is a mistake, like erase your whole hard drive, stuff like that. It does sometimes, however, seem like apps have a mind of their own, which is generally sometimes by design, and sometimes it will become so frustrating when you're trying to make an app do what you want it to do, and you can't figure out why. It will happen to all of you, and don't worry, we'll get through it together. So, if we look at a recipe like chocolate souffle, let's break apart this a little bit, so that you can see the pieces that actually are relevant to writing computer code. First of all, instructions are executed from top down. Code consists of instructions. So those instructions are of a couple of different types, and we're going to talk about those types today. But in general, just like a recipe, you want to start executing those instructions from top down. So whenever you read a chunk of code, and we'll show you today and next week which chunks you read top down, but in general, top down is the way to go. Instructions. Things like brush, coat, set, preheat. These are all the things that the recipe is telling you to do in a very active way. Air conditioning just turned on. Lovely. All right, values. So in computer code, we have this notion of a value. When we talk about data, data consists of numbers like this and other forms of combinations of ones and zeros. But in this case, we want to call out this notion of a value. So in a recipe, it's like the quantities of ingredients that you're working with. 7 ounces, 4 tablespoons, 1.5 teaspoons, 400 degrees Fahrenheit, etc. and so on. So keep that word in mind, value. Types. In computer code, there's this extremely important notion of a type. And for recipes, it's kind of like units. So ounces, tablespoons, teaspoons, degrees Fahrenheit. Every value that we see in a recipe for something is qualified by that. You rarely ever just see a number in a recipe, like 4. It's always for something, right? 4 tablespoons, 4 cups, 4, I don't know, potatoes, or something like that. So that notion of a type is extremely important. This is actually the root of why, of this difference between interpreted and compiled languages, and why compiled languages are so much faster than interpreted languages. So in a recipe, for example, it doesn't make sense to say, mix 3 tablespoons of sugar with 400 degrees. Like, that just doesn't compute in our heads in the recipe. If you ever saw that in a recipe, you'd think that somebody made a mistake in the recipe, right? Like, add 40 degrees to 6 potatoes. That doesn't make any sense. In code, that's the same case. Types have to be compatible. When we're talking about one type of stuff, it has to be compatible with another type of stuff in order to perform operations on them that make sense. So what that means is that a type carries with it a set of meaning, along with it a set of semantics that are only valid for that type. So when we talk about 400 degrees, for example, we talk about 400 degrees in the context of an oven, perhaps, and 400 degrees, you can preheat to 400 degrees, you can change 400 degrees to 350, like there's all these things around the notion of temperature that we have in our minds. Same thing with sugar, or tablespoons of sugar. Tablespoons of volume, so we think about 3 tablespoons of sugar in terms of volume. Anyway, with regards to computer code, it determines what actions we can take on that piece of data. Something like taking 2 numbers and adding them together, for example. In Swift, we have to be very explicit about the types that we're using most of the time, or at least maybe half of the time. So just like in a recipe where you have to say, when you use the number 7, you have to tell the person reading the recipe what that means, 7 ounces, 400 degrees. With Swift, we do the same thing. We actually tag every piece of data with a notion of what type it is. This is important because knowing those types, it's able to write code. Remember that compiling step that we talked about? Creating and generating that chunk of code that's really fast for the iPhone to execute? The reason it can produce that code is because it knows the types of the data that you're talking about. So when you talk about the number 7, it actually knows that the number 7 is an integer. And so when the number 7, the integer, comes along, it knows you can add other integers to it, it knows you can subtract integers from it, etc., and so on. And so then, that can generate this compiled fast code that works really well with the processor on the phone. Okay. Swift is a language, and just like spoken languages, formal languages or programming languages have this notion of syntax. So today, we can read through this later in detail. But today, what we're going to talk about is primarily about syntax. It's primarily about how do you put characters together and how do you write the language in such a way that you can write meaningful Swift code. So in programming languages, in programming languages we're talking about things like keywords, which are specific human-readable words that are meaningful to the language, operators like plus and minus, comments, which are the ability to take any piece of English or any set of characters and drop it into the code and Swift will completely ignore it, that sort of thing. So just like with spoken languages or written languages, we talk about punctuation and words. These are the kinds of things that fit into what a programming language is. So instead of talking about this more in the abstract, I think what we should do is dive straight in and load and open up our first playground file so you can actually start to write some code and see what I'm talking about. So I promised that I would zip this up and drop it on Slack, so that's what I will do.
Why did you zip it?
I'm sorry?
Why did you zip it? It's so small.
It's very small, but it's actually not a file. It's actually a very special folder that looks like a file called a package. So that's actually a folder that does not behave like a folder. It's one of the strangest things that Apple ever did for stuff like this. Windows actually did a better job. They have the same thing, but everything's zipped. So I actually don't think you can email a playground. So did everybody find the playground file? That those of you that are having Git troubles, you downloaded it and unzipped it. Okay, so just double click on that bad boy. This works. Okay, so I'm going to
copy it to the accessible. Just leave it as is.
just leave it somewhere. Yeah, leave it somewhere on your hard drive. It doesn't have to go in. Well, you could. No. Just leave it. We'll copy everything over later. If you don't have Git trouble, you should copy everything into the exercise folder. Yeah, sorry about that. No, you're absolutely right. Because it'll cause trouble. It'll cause Git trouble for you. So
Yeah, later, right? Because
you should do it now because we're going to actually edit this file. So those of you that do not have Git trouble, take all of those playground files and copy them into exercises lesson 3.
and then open them there.
And open them from there. So exercises, lesson 3, and then open them from in there. So I probably already have changes to that made. But I am okay because I will fix it later. So I would just take all of those, copy, and paste, and then open it up from there. That's actually a good policy. All right, so then the question is, can you all read this on the screen up here? Do you need? Actually, don't. Is there a presentation mode for this? Okay. All right, so do all of you see this? The arithmetic playground. Okay. It looks a little bit daunting at first, but it's actually super simple. At least in the vast universe of things that we're going to engage. So what you're all looking at, at least the lesson that this is supposed to talk to you about, is a set of types, values and types that consist of all of the numeric data that we're going to put into an app. So these are things, well, quite frankly, numbers. The way that Swift divides the world is into 3 chunks, and 2 of them are virtually identical as far as you're concerned. The first type that we talk about are integers. So integers are what you would normally think of from mathematics when you hear about integers. So it's positive and negative whole numbers, including 0. In the Swift world, we call these ints, int, int. And they do not at all represent fractional values. So when you're talking about whole numbers, positive and negative, we have integers. The other 2 types are called floats and doubles. Float is short for floating point number, which means that the point here in the number can float wherever it wants, essentially. It's kind of a weird way of naming a data type, but nevertheless, that's practically what it is. Floating point numbers represent all fractional values, so virtually any number that we would normally deal with can be represented with floats. So pi, for example, 1.0, anything that could potentially have a fraction to it. Doubles are just like floats. There's no real way to distinguish between them, as far as how they look. But they're a different data type as far as the computer is concerned. So in the early stages of learning Swift, you won't encounter this difference. But later on, when you start writing user interface code, you will definitely encounter the difference between them. So by default, all decimal numbers that we write will be doubles by default. So what that means is it's essentially twice as large, potentially twice as large as a floating point number. It can hold many more numbers in memory than a floating point number.
What's the benefit of having both floats and doubles?
Doubles take up more memory, and floats take up less. So if you ever encounter a situation where memory is a problem, then that can become a big difference. In the future, user interface code generally deals a lot with floats. So you'll be dealing with data types that are float-like. That's just because of the way it's written. And sometimes it doesn't make sense to use a really heavy data type that is essentially overkill for the thing that you're working with. For example, like numbers on this, coordinate numbers on the screen. Generally, integers or floating point numbers. It doesn't really make sense to use doubles, even though you can. There's no rule against it, and you won't even be punished for it generally. You won't throw an error or anything like that. Yes.
So if you take the same number and say it has like 5 decimal points, and you use that as a double, it'll automatically take up more memory than as an integer?
That's right. Unless it's a 64-bit integer, which they are. So we can dive deeper into data types, but floats and doubles are generally, at least from what I understand, is 32-bit and 64-bit.
And sorry, the default is a float.
Default is a double.
Is a double. Okay.
At least as far as I can tell. I've never encountered a situation where it put me into float land.
Only when creating currencies or applications that work with currencies, because the reason why it uses more memory is because it's a lot more accurate. If any of you guys seen The Office, is it called The Office? That movie. They use floats instead of doubles, and that's why they were able to get away with what they did. So that's a little side note.
Oh, Office Space.
Is it? No, is it Office Space?
Yeah.
I can't remember that. It was like 8 years ago. But you guys know which movie it is.
Right.
So it uses more memory because it's a lot more accurate, and it uses more decimals. So only when working with financial applications.
Right. So the key thing to note is that when you look in Swift and you see a 1 and a 1.0, and you type the number 1, and you type the number 1.0, those are fundamentally different data types. Swift does a great job about figuring out what you mean in various circumstances, but other times it will complain. So that's the kind of thing that we're going to start to tackle today and look for. Whenever we start talking about types, we're going to use this phrase of type. So we can say things like 3 is of type int, or 3.1 is of type float. So when we say stuff like that, that's what we mean. We're trying to give you a value, the number 3, and a type that goes along with that value, integer, or int in this case.
So you see 3.14. That could actually be a double. You're just not seeing the rest of the decimal places. And could it just be 3.14 and infinite zeros, or?
Yes,
or
it could be
like
just
a regular
3.14 and essentially infinite zeros.
Or pi with all of.
Or it could be pi as long as much memory as it will take up. How many decimals of pi can a double hold? Do we know? It's just a lot.
Always forget.
Yeah, I always forget.
The double
We'll find out for you.
The double will hold a lot more.
Oh yeah, absolutely. Okay. Playgrounds. So playgrounds are, again, a convenient place to execute Swift, but also to get information about how the code runs. So playgrounds are useful because some constructs that run in apps that are typically very opaque essentially peer into that and give you data about what's going on inside your code. We call that process introspection. And so it's a great place to actually learn about how code runs. So things like loops, which we're going to talk about at the end of the course, become much less opaque in a playground. The way this works is you write lines of code on the left-hand side, and then on that same line over here, you'll see the result of that computation. So in this case, 1 plus 1, indeed, according to Swift, equals 2. What data type are those ones?
Hints.
Yes, excellent. Yes.
So do you have to like run each line, or because I know in SQL you have to like write the query and then run it, and, and that's like the scripted thing that you were talking about, right?
That's right. That's right.
So you don't need to run each line; it just will.
Yeah, it just figures out that you've changed something, and now it runs it.
Okay.
We'll warn you. Sometimes playgrounds can be a little bit unstable, but if that ever happens, we will help you get out of that state. But yeah, it is constantly watching you, and every time you make a change, it will update what's over there.
So is this a place where, as you're building different functions throughout your classes, you can just keep some tests? It's a quick way to test and see if your code is returned.
Yes, in fact, I do that a lot. Like if I'm extending some piece of code that I've gotten off the internet and want to know how it works, I'll paste it in here and play around with it first.
Do you place the whole code, or just the like? Do you actually do the whole code too?
No, well, I mean, it depends on how much code you're talking about. Typically little chunks. If I'm trying to figure something out, it's usually much easier in a playground, much faster than having to like put it in your app, run it, watch it break, etc.
Also keep in mind that you can actually import files into your playground. So if you have your logic in a Swift file that's already part of the interface builder, you can actually import it here and use those functions that are inside that.
Yeah. Just something that once we start to show you how to take Swift and the stuff that you've done in interface builder put them together, it's going to be an really important piece of code. All right, so this is a point that we're going to go over now, even though it's a little bit heavy, but it's super convenient to be able to write expressions like 1 plus 1 and have the playground evaluate it for you and show the result on the right. However, that doesn't work in an app, strangely enough. You can't go into an app and write 1 plus 1 just on a naked line and have it work at all. So there's this function the first function that you're going to learn is this function, println. And I'm going to explain the syntax around this function right here, because you're going to see it in these playgrounds. And the reason why this is important is because this is the function that you're going to use later on in apps to write these results in a running app. Like you're going to write println, it'll show up in Xcode in the debug console down below. So you'll actually be able to say, like, create a button, and then tap on the button, and then it'll start printing stuff it'll start outputting into the console. So even though it's a bit premature to talk about this function, I want you to know what it means because it's in the playgrounds. It's a function that prints values both in playgrounds or to the console in Xcode. The syntax that you're looking at, which is this name and these parentheses and any value inside, is called calling the function. And the point of the name of the function when we say it out loud is println. So whenever you hear me say println, it means these set of characters, println. Okay. So let's open up the playground and see exactly what I mean. So,
Does it make a new line?
I'm sorry? Yes, it does. Yes, it does. Okay, so here we're going to talk about the semantics and syntax of operations around our numeric types, integers and doubles. So here is just a place where you can start to play around with how this works. If you have your playground running, you should notice at the top a bunch of English that is of lines that are all preceded by 2 slashes. These are called comments. They're part of every programming language that's out there. They might have a different syntax, but the syntax for Swift is generally 2 slashes. And then afterwards, on that line, you can write anything you want. So this is a technique that we're going to use in order to annotate our code with English so you can remind yourself what's going on. So if you see down here, these are all of the operations that you can perform on integers and other numeric types like floats. So what I would like you to do is just change these values to some point. So 1 plus 1, change it to 1 plus 2, and watch how Swift updates and recomputes that for you. Instead of 1, type in 100. You get 102 on the right. 20. Add another 1. 300 plus 20 plus 1. All I want you to do is just try to get used to typing in these expressions. These expressions are the first, every line that you see from top down here, everything that's not a comment, we call an expression. So just like in mathematics, we talk about a mathematical expression. Here, these mimic probably, hopefully, what you're used to seeing from your math courses back in the good old days of elementary school. Great thing about Swift, tries to mimic what you already know as closely as possible. So, this is integer addition at the very top. The next one, double addition. So each one of these is a double. So you can start to type
What happens if you...
expressions like that. Sorry?
What happens if you do 19.1 plus 10?
I don't know. Try it. Try it and see what happens. So one thing to note about the playgrounds. An integer plus an integer is an integer. A double plus an integer is a double. Because doubles are more complicated than integers.
Integer plus